Welcome. Thank you for joining us for today's webinar, Cooling Strategies for High-Power Electronics Cabinets, presented by Advanced Cooling Technologies and Tech Briefs Media. I'm Bruce Bennett, editor at Tech Briefs Media, and I'll be your moderator today. This webinar will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by using the Ask a Question box on your screen. Our speakers will answer as many questions as possible at the conclusion of the presentation. Those questions not addressed during the live event will be answered offline. To view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce today's speakers. Seth Ryberg is a sales engineer responsible for business development at Advanced Cooling Technologies Incorporated, promoting advanced thermal technology and product sales across the western and midwestern U.S. Since joining ACT, he has worked across much of the defense, aerospace, and industrial sectors, helping to diagnose thermal issues and select custom thermal management solutions for customers. Seth graduated with a BS in Mechanical Engineering from Penn State University. Dan Rice is the manufacturing manager at Advanced Cooling Technologies, responsible for production of a diverse range of thermal solutions. With over 10 years at ACT, he has worked as a lead engineer for several key ACT initiatives, including the development of ACT's sealed enclosure cooling product line. Dan graduated with a BS in Mechanical Engineering from Penn State University. Now that you're familiar with our speakers' qualifications, let's begin today's presentation.
Welcome to Advanced Cooling Technologies webinar on high-power electronics cabinet cooling, a particularly hot topic in the industry. Today we will discuss how to best service this niche market with the optimal thermal technology to provide performance, reliability, and efficiency for these types of systems. To give you some background, ACT is a custom advanced thermal management solutions company located in Lancaster, Pennsylvania. We are comprised of approximately 150 employees who uniquely specialize in heat transfer for a wide variety of markets and applications. Today, we will discuss the following. First, we will go through the background of the industrial control cabinets industry and the current trends that we see that accompany some of the challenges. After highlighting these challenges that affect thermal performance, we will take the next step in identifying the issue by highlighting numerous ways to calculate internal heat load of these applications. Third, we will highlight ACT's capabilities in the form of technologies we offer to solve these types of thermal issues. This includes ACT enclosure coolers, high K plates, and loop thermosyphon technology, all with respective relevant experience associated with it. Lastly, we will take time to summarize and answer any questions the audience may have at that time. In today's industry control cabinets applications, there are many challenges that may arise. The first one being higher component density, which corresponds to more internal heat load that must be managed. The second being that manufacturers are trying to shrink cabinet size to achieve volumetric efficiencies. The third one is that requirements for proper isolation from the elements are ever present. In most occasions, any exposure to the extreme elements could result in a high risk of failure. This is where ACT comes in with these types of solutions. Enclosures heat loads come from two main sources, an internal heat load as well as an external heat load. Internal heat load can be defined as the electrical components and equipments that are incoming to that enclosure. The external heat load is the ambient temperature outside of that enclosure. The first method we will discuss that calculates the total heat load as well as the internal and external heat load is the input-output method. This approach details how to find the total internal heat load by taking the input and outgoing heat loads. First, we will access the total number of electrical input conductors, voltage in amps entering the enclosure. By doing so, we'll take the quantity of these components and multiply that by the voltage in amps to get the total input. Next, similarly, we will do this with the number of conductors leaving the enclosure to find the external heat transfer load. Lastly, we will find the difference to calculate the total internal heat load via this calculation. As you can see at the bottom of this slide, here's one example where we're taking 2 input conductors at 230 volts and 11 amps, 7 input conductors at 115 volts, 6 amps, and 1 input conductor at 230 volts, 5 amps to find a total incoming heat load at 11,040 watts. The outgoing conductors can be calculated in a similar fashion with 9 of them at 115 volts and 10 amps for a total of 10,350 watts. Taking the difference of these two values, we calculate the total internal heat load to be 690 watts. The second method in which we can use to find the internal heat load of the box is the component heat load method. In terms of this method, you will find on this slide general heat loss values of commonly integrated components of electronic cabinets such as power supplies, drives, contactors, transformers, etc. With the general efficiency and manufacturer specifications of these types of components, we can easily calculate the power loss of each module and then add them to find the total internal heat load. On the next slide, we'll discuss how to utilize these to calculate an example of internal heat load. For this example, this motor drive application had a few different types of electronic modules present. In this example, there are commonly found components including a VFD, a contactor size 1, transformer, power supply, and indicator lights. Now taking each quantity, multiplying it by the power parameter in watts, by its efficiency, we calculate each respective heat loss of each component. Adding them up will give us the total internal heat load of that enclosure, which will ultimately determine what type of thermal solution will be needed. Now we will look to speak to the technologies that ACT can design and procure to solve these types of common thermal challenges. The first technology we'll look to talk to is ACT's sealed enclosure cooler line. Now in this product line, there are 4 different configurations, both servicing an above ambient as well as below ambient case as well. The above ambient solutions include the heatsink coolers HSC product line as well as heat pipe coolers HPC product line. And I should define what above ambient versus below ambient cases are themselves. In the above ambient cases, the inside enclosure temperature is greater than the outside enclosure temperature. For below ambient cases, it is just the opposite. The inside of the enclosure temperature is less than the outside of the enclosure temperature. Now with these product lines, there are a variety of different options we can talk to as well. Now this includes introducing a thermoelectric, as we do have that product option as well as a low noise option, also dubbed the LNC product line. Moving into ACT's sealed heatsink cooler line and describing what they actually are. This series of enclosure coolers offers a passive sealed enclosure cooler design consisting of 2 advanced high-performance aluminum finned heat sinks bonded to opposite sides of a common efficient heat transfer mounting plate. Fans are used to transfer heat effectively across these fins. Again, with this type of product line, there are various sizes and options to touch on, starting at approximately $590. The model number, if you are wondering, HSC22, HSC45, or HSC68, corresponds to a certain thermal conductance value. For example, if your application has a 20 degree C delta to work with and you are using an HSC22 to help cool that application, you would get approximately 440 watts of heat dissipation capability. This calculation similarly works with any delta with any of the model numbers to get not only the specific configuration you need, as well as the number of units you may or may not need. To go into further how these types of solutions operate, first we'll take the inside of the enclosure portion. The HSC's internal fan blows the hot enclosure air over the high-efficiency bonded fins. The internal enclosure's heat is rejected to the outside of the enclosure via a common sealed heat transfer plate. On the external portion of the HSC model, the external fans blow the cool ambient air over the external high-efficiency bonded fins, reducing the internal enclosure temperature. Next, we'll look to talk about heat pipes and their operation as thermal superconductors. Heat pipes are comprised of three basic components: a wick, an envelope material, as well as a working fluid. The expertise of heat pipes lies in their two-phase heat transfer capability. In this capability, we are taking advantage of the latent heat of vaporization of that working fluid in the evaporator area. We are then transporting heat effectively to the condenser region, where the working fluid is condensed back into the wick and then returning to the evaporator area via capillary action to create a heat transfer cycle. Again, we'll talk about how this is incorporated into the next type of enclosure cooling thermal solution, but here we are able to promote the seal, effectively encapsulating heat transfer between certain sealed areas. Next, we will talk about ACT's sealed heat pipe cooler line, the HPC technology. Similar to HSC, but now containing heat pipes that transport heat effectively between a common base plate and fins. These fans blow air carrying internal heat load across these same fin structures, while the heat pipes pick up heat from the internal portion fin structure and transfer to the external fin structure, where ambient air is again blown across that fin structure to remove heat from the system. Again, similar to the model number corresponding to a certain thermal conductance value of the HSC product line, if your application has a 20 degree C delta to work with and you're using an HPC 80, you would get approximately 1600 watts of heat dissipation capability. Again, this calculation works with any delta with any of the model numbers to get not only the specific configuration you need for your application, as well as the number of units you may or may not need. Again, expanding upon the operation of this device, we'll walk through again, starting in the enclosure, going through the process of heat transfer to the external portion of that enclosure. Hot air from the enclosure is blown across a fin structure again to the first portion of heat pipes, where heat pipes start operating and removing heat from that airstream. Cooled air is then returned to the enclosure as the heat is transferred to the external portion of that HPC model. Using a fan, cool ambient air is blown across that heat pipe fin structure and exhausted to the ambient air. Next, we'll talk about ACT's thermoelectric cooler solid-state enclosure air conditioning unit. Again, this is for the below or sub-ambient cooling market. This enclosure cooler introduces a thermoelectric cooler that can be included within different forms of the unit itself. This key operation, again, is used for sub-ambient cooling itself. There are similar options in this unit as the HSC and HPC models, which we'll go into detail later, but it does have a few unique features I'd like to highlight for now. With this Peltier cooler incorporated into the unit, there is a built-in adjustable thermostat. You can also acquire an optional condensate drip pan for this unit, as well as there is an optional heating mode for this unit as well. Next, we will introduce ACT's value add role when it comes to designing and building these types of enclosure coolers for the industry. In this technology family, we here at ACT feel that we have a unique perspective in understanding cabinet cooling thermal issues and how to approach solving them. In terms of enclosure cooler options, there's a variety of different things we can do to utilize these types of systems. We're not just locked into the specifications that you saw in previous slides. With this, there are custom designs that we can look to procure and design for your application. One example itself is mounting your modules directly to a portion of that HSC or HPC model for limited volumetric parameter applications. In this example, we have an HSC 22 model to a customer that mounted their IGBT module directly to the base plate itself. This base plate, again, still comprises the sealed wall of the enclosure, but provides a direct route of heat transfer to cool that module. In terms of other options, we have various coatings for various NEMA ratings, ranging from 12, 3R, 4, and 4X. There are also varied voltage requirements that can be incorporated. 12 volt DC, 24 volt DC, 48 volt DC, as well as 115 volt AC or 230 volt AC. With these types of modules, if coatings are not enough, we also have custom rain hood protection units that can be incorporated to the assembly, as well as a flush mounting kit for applications that can't protrude too much into the enclosure. The next slide is highlighting our custom engineered solutions for various relevant experience. The first application is for a mining application, a coal mining application, cooling of drives that power a circular cutting mechanism. In this application, we incorporated and retrofitted our units versus a competitor's for heat pipe-based heat exchanger HPC model units. The middle picture highlights a high voltage protected version of the HSC 22 model. This is unique in that we used a unique bonding effort to achieve more grounding of the unit itself, implementing a 90-degree heatsink core and providing custom color on a custom fan cover that removed grates originally from that HSC model to prevent arc flash from occurring. The third application found on the right side of the slide is a design for an outdoor satellite receiver application. ACT plans to design and build a custom enclosure with integrated thermoelectric cooler units in the walls of that enclosure. The next slide highlights ACT's online resources, as this is an easy, simple way to access not only information, but assess your application's feasibility from a high level. In this website, we have not only product overviews and various product pages containing technical data, as well as an easy selection tool and ordering online tool as well. If in need of different videos in terms of installation as well as technical videos, along with data sheets and/or models of the units itself, these can be found in the technical resources section. Note that for the EC selection tool, you will gain conductance through the body of the enclosure. So if you're choosing a unit that is on the edge of the power transport capability, take into account the inherent conduction of the enclosure itself that you will gain in terms of the heat transport ability. Moving away from enclosure cooling units, we will next talk about high K plate technology. This technology is called, again, high K plate, standing for high effective thermal conductivity plate technology. This technology incorporates heat pipes embedded into a plate, in this case, aluminum. Now, implementing these types of heat pipes in this aluminum plate increases the thermal conductivity of spreading heat efficiently to the most effective cooling location. If we were to compare this against copper or aluminum base material, the aluminum has a thermal conductivity of about 175 watts per meter K, the copper 385 watts per meter K, but the high K plate technology anywhere between 500 to 1,200 watts per meter K. Now, this comparison may sound astounding, but we are maintaining, again, the similar basic structure, strength, and weight as that aluminum plate itself, just by implementing heat pipes within. The example on the right side of the page there is an existing retrofit for heat pipes that was completed years ago. A customer came to us with their aluminum plate on the left with 3 discrete hot spots on that plate. ACT took a look at this application and changed nothing about the plate, but incorporating and embedding heat pipes into that aluminum plate itself, and in doing so, increased the thermal conductivity and reduced component temperature by 20 plus degrees C. Other relevant experience utilizing this high K plate technology, specifically within the cabinet cooling realm, can be mounted directly to the base of an IGBT module, for example, to better isothermalize that module itself. Again, this same thermal technology can make up the structural seal and optimized thermal solution for that application. It can also move heat to the most effective cooling location, in this case spreading throughout the fins. This example specifically was for a shipboard electronics cabinet that, with the help of embedded heat pipes, transferred heat from 6 IGBT modules directly mounted to the plate to the fins very efficiently, in the 100s of watts of heat transfer range. Again, with this type of technology, there are just certain design considerations that include the number of heat pipes being embedded, the layout and geometry of those heat pipes specifically, as well as the fin optimization geometry. Next, we will talk about loop thermosyphon technology. This unit utilizes 4 basic components: an evaporator body, a condenser body, a working fluid, and separate vapor liquid lines. Here, we are using the thermosyphon effect to move large amounts of waste heat at low thermal resistances. Heat generated by power electronics causes liquid within the attached cold plates to evaporate. The expansion of this fluid as it changes phase from liquid to vapor creates a stirring motion that increases convection and subsequently heat transfer efficiency. The same expansion of vapor in the evaporator combined with the condensation of liquid in the condenser generates a gravitational pressure imbalance that naturally maintains fluid circulation between the condenser and evaporator. A substantial amount of waste heat is transferred using this natural circulation since the latent heat of evaporation of the working fluid is large. The result is an extremely high-performance cold plate that requires no moving parts. On this slide, there's one example of implementing loop thermosyphon technology based on a table of requirements. This is a unit for a medium voltage drive application, which all requirements were achieved. To touch on a few key parameters here in this table, the power needed to dissipate was in the 11 kilowatt range with an operating temperature from negative 55 degrees Celsius to positive 50 degrees Celsius. There was a need for dielectricity of the working fluid for a lack of risk of failure with no moving parts. A loop thermosiphon approach satisfied all these requirements and tested optimally for this customer. All in all, ACT feels that we are a one-stop provider of thermal technologies that service the high-power electronics cabinet cooling industry. In terms of needing thermal alleviation, these are the preferred routes to go while minimizing the amount of active components in the system with enclosure coolers, but staying completely passive on the heat transfer device itself, high K plate, as well as loop thermosiphon technology configurations. Please contact ACT to learn more about how your application is applicable in using one of these thermal solutions for enhanced performance. Thank you for your time today. Are there any questions from the audience we would like to discuss at this time?
Thank you, Seth, for that most informative presentation. And before we get to the first question, I'd like to remind our audience that if you have a question, you may submit it by simply using the Ask a Question box on your screen. So, first question. What are the benefits of using an ACT enclosure cooler compared to an air conditioner?
One major difference between ACT's enclosure coolers and standard vapor compression coolers is that the ACT enclosure coolers do not require the use of any refrigerants. Also, unlike an air conditioner, the ACT enclosure cooling designs do not use compressors and expansion valves, so the energy consumption is going to be less for an ACT enclosure cooler. And because ACT enclosure coolers have fewer moving parts than air conditioners, they have a much higher reliability in the field.
Thank you, Dan. Second question. Can the HIC plate technology survive outdoor enclosure elements when spreading heat?
Yes, ACT enclosure coolers are designed to operate in harsh environments. Our standard NEMA 4 offering comes with powder-coated aluminum covers, which hold up well to outdoor use. For extreme conditions, our NEMA 4X line uses 316 stainless steel covers, and all aluminum surfaces are protected by an electrofin coating.
Thank you. I have a densely packed enclosure and want to use an ACT enclosure cooler, but I don't have the space to mount to penetrate the box. What can I do to accommodate the unit, and how does this affect installation?
For applications where there's no space available within the enclosure, ACT offers a flush mount kit that will allow the enclosure cooler to be attached to the side of the cabinet without any protrusion. The flush mount kit is suitable for use in NEMA 4 and NEMA 4X applications and is installed in a similar fashion to the ACT enclosure cooler.
Thank you. I'm afraid that's all the time we have today. I'd like to thank Mr. Ryberg and Mr. Rice for giving us such an enlightening presentation and answering those questions. And I'd like to thank today's attendees for participating. That concludes today's webinar, sponsored by Advanced Cooling Technologies and TechBriefs Media.